Thermite reaction is based upon the combustion of a metal in the presence of a metal oxide. As the oxygen necessary for combustion is provided by the metal oxide and not the environment, this combustion can even occur underwater. In fact, the most common use of the thermite reaction is for underwater welding. In our case, we used iron 3 oxide and pure aluminum. As the reaction occurs, the oxygens are transferred to the aluminum, liberating a lot of energy, which melts the products and most anything nearby.
So we made a uniform mixture of aluminum and ferric oxide with micron particles inside of a glass bottle. The uniform mixture looks like this on a microscale, with both phases in the solid phase produces a K value of equal to 1. The delta H is calculated and is highly exothermic. It was calculated by summing up all the stoichiometric values times their heat of formation, resulting in negative 850 kilojoules per mole.
In order to prepare iron oxide, we burnt steel wool, which due to its low carbon content is almost pure iron. As the steel wool is incredibly fine, it burns quite easily due to its large surface area to volume ratio. It turns out one of the easiest ways to get pure aluminum is to break open an Etch-a-Sketch. This is easier said than done, however. Luckily for us, Dylan was able to finally defeat the Etch-a-Sketch.
Ah! That was a good one.
After mixing the iron oxide and the aluminum in a plastic container, we attempted to ignite it. We believe the reason the mixture failed to ignite was due to the large size of the aluminum particles from the Etch-a-Sketch. Their size resulted in a relatively small surface area to volume ratio, which hampers the reaction rate. In order to fix our problem, we ordered 30 micron aluminum powder through Amazon. Using the new aluminum powder with the iron oxide gave us a lot better results. In order to test our new mixture, we put it inside of glass bottles. We hoped that the heat would melt the glass bottles from the bottom up, resulting in a cool deformation as the mass of the top of the bottle pushed down on the bottom. Whenever we actually attempted to do this, however, the bottle simply exploded. The explosions occurred because of the buildup of pressure within the bottle. The incredibly hot temperature heated the air within the bottle, increasing its pressure. This then popped the bottle because the air could not escape out through the top quick enough to relieve it. Despite the explosion of the bottle, the bottom still remained intact. The procedure was repeated in various different bottles in order to see if any different effects could be obtained. These additional trials were slowed down in order to better observe the effects of the reaction within the bottles.